repeated squaring technique. Yeah. So here I like to talk about two interesting techniques. Yeah. And also in our quiz questions, there are two questions related to these techniques, two questions. The first one and the last one. The first question number one and question number 10 in quiz 1 related to these techniques. Yeah. All right, so let me start the first technique. It's called the repeated squaring technique. So what's that? Yeah. So let me describe the problem first. Yeah. All right, the title, evaluate monomials based on square structure. All right. So what's the monomial? Okay, first, yeah. So it's we just finished studying polynomials, right? Yeah. But the monomial, it's a very simple form. Only one term, x to the nth. So that's the monomial. All right. Yeah. We can evaluate polynomial using the Horner's rule. Yeah. So why we need to look at a much simpler form, monomials. All right. Yeah. Here, something is interesting here. Yeah. All right. So here the monomial. Yeah. If we use the usual way to do evaluation, x multiplication between every two operands, yeah. Multiplication operands. Yeah. Okay, so if you count one, each dot corresponds to one multiplication, and you have total n operands of, yeah, n operands in between n minus 1 dots, right? So that corresponds to n minus 1 multiplications. Right? Yeah. The question is, can we do better than this? Can we do better than this n minus 1 multiplications? Right? Can you see a better way to find the value of this power form, power function, power form in a much faster way? That's interesting, right? That's interesting. Yeah. The answer is yes. There is a much faster way we can use to find the value of this power form. Yeah. All right. So how? Yeah. How to do that? Yeah. All right. So here, there is a smart idea. Smart idea. Okay. Yeah. So here, let me talk about the idea first. Idea. Yeah. Okay. Yeah. Idea. Let me start with some high level, the general principle that we use in our daily life. General principle. Okay. In our daily life, we want to do things efficiently, in a productive way. All right. Yeah. So when we want to do something, when we want to complete some tasks, we need to use resource, right? We need to use, a lot of resources. We know the resources. There is some cost associated with resources. It's usually resources not free and sometimes pretty expensive. All right. So you don't want to waste your resource. So you want to save your resources as much as you can, right? Yes. So in our daily life, in our mind, we tend to save the resources when we need to solve some problems, right? Now, here we take that approach, that kind of approach, okay? Yeah. So the idea is reuse the resources. Okay, yeah. So here, what I mean, the resources here, I mean something with useful values. So I treat as resources, okay? Something, useful, yeah. And not free, we need to pay, right? So not free, we need to pay on the resources. So we want to save the resources, right? Yeah. So here, now, let's look at the calculation part. Calculation, this power form, the general power form. We need to use resources, right? Yeah. So you need to pay necessary costs to do the calculation here. All right, yeah, here. When we do that, we try to reuse the resources we need. We pay to get the resources. We need to reuse the resources we already paid. That idea, okay? All right, so let me show you a simple example here. All right, now, in this example, we want to calculate x to the fourth, this power form, this monomial power form, x to the fourth. All right, yeah, okay. If we use the old way, yeah, old way, x dot, four x's, 4 copies of x, right, with 3 dots, then it gives us 3 multiplications. All right, so now new way, okay, yeah. So new way, we try to use this idea, reusing the resource idea here. Okay. All right, yeah. X to the fourth, this time, x dot x, 1 multiplication. 1 multiplication gives us x squared term, right? X squared term. We have the value. Okay, we already have this value after calculation, after first round calculation, right? Yeah. Okay, we have it. Or this item, after we get a square, we already paid, right? It's not free, right? when you do calculation, x times x, you need to pay something, right? Yeah. Although you may feel it's very cheap, yeah, but you need to pay something here, all right? So it is paid. So we have that value in our hand. So the question, do you want to pay it again? If you already have the value, the next time when you need it, do you need to pay it again? No, you don't need to pay. You have it. You just reuse it, okay? It is already in your hand. You just use it directly. Don't pay it another time, right? Okay, so now the next time, because x to the fourth, so we have another x squared, but the second time we don't pay. So we do not pay here because we reuse it. We use our existing version copy, right? We use something we have paid, okay? Do not repay it. All right, now, based on this understanding, let us count how many multiplications do we need, right? Yeah. Multiplication one, the first time we pay it, all right, pay for it, one multiplication. Then second time here, we have to pay two multiplication, but we do not pay this copy for this copy, all right? Yeah, that copy we can save. We do not pay, all right? Yeah. So now, as a conclusion, you can see we do the reduction. We only need two multiplication. Yeah. All right, we improve it. So think about that. So here, the reason here we can save a few more multiplications, you can see, because we explore the square structure. We take advantage of the square structure, okay? In other words, if we can find squares, then we can save some multiplications. So that's the conclusion from this example. Okay, yeah. All right, so, a question. Are the X in the old way being paid? Oh, yeah, all right, yeah, good, yeah. So your question, are the X in the old way being paid for every, or because here, what do we say pay? We mean when we do multiplication, we pay something. Think about that. When we do multiplication, all right. So the old way, the copy, each copy, we do not do multiplication, right? Each copy, we grab it, we put there. So here, let's talk about, one multiplication corresponds to the, the basic cost we need to pay, right? Pay for what? Yeah. What, let's say this way, each multiplication is not free. We need to use computing resource to do multiplication. That's what we mean, we pay. But all the way, each X, if you only look at each X, there is no multiplication involved. That means we do not pay anything, right? Yeah. So that's why we do not say we pay. Okay. Yeah. All right. Yeah. So we just put there. Yeah. All right. Now, next. So this idea, let us generalize to the form. So here now think about, we can consider still power form with n power of 2. How about that? Power of 2, that means n equals 2 to the kth power. Okay? Yep. Because in that case, we can take advantage of that square structure again, and again for k times. How about that? K times. How about that? Okay? Yes. All right, so now x squared the first time, 1 multiplication. All right. X to the 4th equals x squared times x squared, right? So you can see 2 multiplications, all right? Yeah. X to the 8th, look at that. X to the 4th times x to the 4th, all right? X to the 4th, the first one, we pay two multiplications. That's the cost we pay, all right? Then we just add 1 for the dot in the middle, but the second copy x to the 4th, we reuse. Second copy, we can reuse, all right? So then we only need to add 1 more multiplication. That's 3. Yeah. Similarly, x to the 16th, x to the 8th times x to the 8th. The first copy of x to the 8th, we pay 3 multiplications. The second copy reuse. Then the dot in the middle, we have to pay that cost, right? So the answer 4 multiplications. All right? Yeah, that's enough. We can go until we reach x to the power of 2 to the kth. Yeah, 2 to the kth power. X to the 2 to the k minus 1. First copy, dot, x to the 2 to the another 2 to the k minus 1 copy. The first one we pay k plus 1. Yeah, just the same number as the exponent. All right. Then add 1 in the middle dot and reuse. So the answer k multiplications. How about that? So you can see we can save a lot. We can save a lot. Yeah. So here, let's consider this question. How much? How much do we save? Here, okay? Yeah. Let me use a simple example to show how much do we save. Okay, yeah. Here I take a special n, power of 2, n equals 1024. You're familiar with this number, power of 2, right? 2 to the 10th. So it is a famous power of 2. 2 to the 10th. All right. Then now comparison all the way. Okay, all the way. Without reusing the resource, that all the way. Okay, without using resource all the way. We need 1023, the degree number minus 1, 1023 multiplications. Okay, yeah. Now a new way, reusing resource. Okay, yeah, new way. In other words, without doing redundant calculation. No. New way, k equals 10, right? In this particular example, this k corresponds to 10. That means 10 multiplication. How much you saved? From 1023 to 10. Is that big save? Look at that. Is that big saving here? Right? Yeah. Even you do not look at that 1023, more than double that 10, right? Look at that. But there is a big 1000. Look at that. That saving is huge, right? Yeah. Look at that. Okay. Yeah. All right. Yeah. This example, you can see our new method. Yeah. We call it repeated squaring. The name repeated squaring. Yeah. The new method. Much better, right? Yeah. Okay. Then now you can answer question 1 of quiz 1 better, right? Question 1 of quiz 1. The higher the degree, the smaller the number of multiplications, right? Here, the higher the degree, look at that. The higher the degree, 1000 something, pretty high, right? The number of multiplication using this new technique, only 10. Only 10. Look at this example, okay? So when you try to answer question number 1, use this example there, all right? So here the degree more than 1000, greater than 1000. But think about, you have a polynomial a0 plus a100 x to the 100. That degree only 100. This 1000 is much higher than the 100, right? But this polynomial, you need 100 multiplication, right? But here you only need a 10. Can you compare? Consider this example here, right? Yeah. All right. Yeah. Here, implementation recursively, we can implement this idea, using a recursive function call. Yeah, but here I do not have space. Yeah. So I need to later I talk about this idea. Okay. Yeah. Recursion idea for implementation. All right. All right. So next topic, repeated cubing technique. Similar, yeah. The squaring way, can we push to another special structure, cube structure? Square to cube structure. So we can do the same thing, still reuse the resources. Yeah, but here the only difference is this time we consider cube structure. Cube structure. All right, so let's look at the first cube structure. Still monomial. Okay, still monomial. Yeah. For our first example, cube structure. Cube structure, we know here we cannot save anything. Yeah. Here, the first time we do cube, we need 2 multiplications. Okay. All right, so the second time, another cube structure. The second time, let's consider x to the 9th. Another cube, yeah. So x to the cube times second copy of x cubed, third copy of x cubed. Okay, now let us count the number of multiplications we need to calculate x to the 9th, that powerful. Yeah. The first copy, we have to pay 2 multiplications. All right. Then this dot 1, the second copy of x cubed, reuse. Reusing, okay? Reusing idea, reuse. The third copy, reuse. All right, yeah, but another multiplication here. So now you can see we need 4 multiplications. All right, yep, 4 multiplications. Similarly, we can go further and further, yeah, and we consider x to the n with n power of 3 structure. So that means n equals 3 to the kth. This power form, okay, yeah. Then x to the 3 to the kth. The first copy x to the 3 to the k minus 1 dot, second copy, third copy. All right, yeah. The first one, based on our, experience, we need to pay how much we need to pay. All right, how much we need to 2 times k minus 1 multiplications, right? Look at that. 2, yeah, because 2 dots, okay, yeah, to the k minus 1, okay, yeah, all right. Then 1 multiplication for the dot, another multiplication for the second dot, okay, add 2 more, so the answer 2k multiplications. Okay, how about that? Okay, so here you can see based on these two cases, power of 2 case, power of 3 case, 2 cases. Yeah. So based on the structure, square structure, we use repeated squaring technique. Cube structure, we should use repeated cubing technique. Okay, then we can save a lot of multiplications. All right, yeah. All right, so here there are 2 techniques we can use. Yeah, right. Repeated squaring, repeated cubing. Right, yeah. All right. So here, look at, so here, another example I like to show you. Yeah. Let's consider this example, x to the 27th. We know this is a power of 3. 3 cubed, all right? Yeah. The structure, power of 3, we know repeated cubing should do better, right? Repeated cubing should do better, okay? Yeah. So based on the method we use here, 2 times 3, 6 multiplications, right? By repeated cubing, we need 6 multiplications. Yeah. But people can still apply repeated squaring, right? Yeah. So how about repeated squaring way? All right, yeah. Yeah. All right, so let's try repeated squaring way. Yeah, 27, okay, yeah, equals 16 plus 11, right? Because 16 is a power of 2. Yeah. So we try to write this n number, exponent n number, as a sum of power of 2. Yeah. But 11, let's continue to write power of 2. 11 equals 8 plus 3. 8 is another power of 2. Okay. 3 equals 2 plus 1. So you can see power of 2, sum of power of 2. Then we can apply repeated squaring technique. Okay. Yeah. So x to the 27th equals x dot x squared dot x to the 8th dot x to the 16. Yeah, that's the squaring based method. Yeah, square based method. Okay, yeah. All right. Yeah. So in order to find x to the 16th, we need to do 4 multiplications, right? Yeah, so let me do not write everything. 4 multiplications. But if you span 4 multiplications, you should get this term and all the smaller power of 2 terms, right? All the smaller power of 2 terms. All right? Yep. So when you pay 4 multiplications, you have all values in the parentheses. Okay, yeah. So you don't need to repay. All right, only pay once. Yeah. Then you need to pay extra multiplications for 3 dots. 1, 1, 1, 3 dots. So the answer for this method, 4 plus 3 equals 7. See, 7 here, but repeated cubing, 6 multiplications. You can see in this example, repeated cubing performs better than repeated squaring. The reason is simple, because the n has the intrinsic structure, cube structure, intrinsic. Yeah. So the repeated cubing method takes advantage of the intrinsic property, cube structure property. Okay? Yeah. Square structure, it's not intrinsic structure in this 27 number here. So we have to use a little more cost. If you really want to apply repeated squaring, you need to pay a little higher cost, because the structure may not be quite compatible, right? Square structure and cube structure, they're not that compatible. That will make you pay a little high cost. Okay, yeah. So that's the problem. All right, yeah. So now you get the idea. When n is a power of 2, you should use repeated squaring. When n is power of 3, you should use repeated cubing. That's simple. That's straightforward relationship. Okay. All right. So let me write a conclusion here. That's the conclusion. Okay. N equals power of 2. Simple. Repeated squaring. All right. Yeah. N equals power of 3. Repeated cubing. All right. Yeah. That's simple conclusion. Okay. Then you may ask, if n is not power of 2, not power of 3, something between, which one is better? Right? Yeah. So the answer is not that straightforward. The answer much more complicated. Okay. Yeah. Yeah. All right. Yeah. So here. All right. Yeah. Let me. Yeah. I need to see the time. Yeah. You know. Yeah. So here, all my electronic devices are blocked. You know, I couldn't see the time. Yeah. Yeah. All right. Yeah. Yeah. All right. All right. Yeah. So I can control, you know, how fast I go. Yeah. All right. Oh, yeah. Now 6:20, 45, 20, 10. Yeah, 25 minutes. Yeah. All right. All right. Now repeat cubing recursively. Now I like to talk about implementation. Repeated squaring, repeat cubing recursively. Yeah. When you need to write a implementation, what you should do. Yeah. So let me do 2 together. Okay. On this slide, let me implement both. Right. Repeated squaring and cubing together here. Okay. Yeah. All right. So repeated squaring here. Repeated cubing here. Okay. Their implementation, the way are very similar. Yeah. So idea is very simple. All right, yeah, let me write this way. Yeah. Oh. All right. Because we need to implement recursively, we need to define recursive function here. We need to call this function by itself. Okay, yeah, recursion. Yeah. Regarding the recursive algorithms, we will study in much more details in our module 3. Module 3, we will spend a lot of time studying recursive algorithms. Yeah. But here we need to implement these two algorithms recursively. Yeah. All right. So let me write the function name. First, we need to define repeat square. Yeah, let me call the function name n. Okay, how about that? Yeah, that's the function definition. Okay, yeah. All right. When we start, yeah. Yeah, we know because yeah, when we start, yeah. Yeah. All right, so okay. Yeah. So let's declare some variable. Initialization answer equals 1. Okay. Some intermediate variable power equals 1. All right. Yeah. Okay. All right. Then, based on an even and odd, yeah. So here, all right. Okay. Yeah. Yeah. Let's say the power. Yeah. Because the squaring, we explore the squaring structure. The power equals recursion call n over 2. How about that? Okay, n over 2. Yeah, because we split. Yeah, this is a recursion call. All right. Yeah. Okay. All right. Then, if n mod 2 equals 0. Okay, that means it's an even number. Then the answer equals PWR times PWR. How about that? Just add one more multiplication. Yeah, we already compute PWR. All right, that, you know, this number. Yeah, and we reuse it here. The second PWR, we just use the older value. Okay, the second one reuse. Okay, yeah, but else means n is an odd number. So this time answer equals, yeah, sorry, x. Yeah, other than n, we need to pass another, you know, our variable x. Okay, x times PWR times PWR. We need to multiply an extra x. Yeah. All right. Then return answer. How about that? This is the definition. repeated squaring definition, recursive function. Okay, yeah. Similarly, repeated cubing, we can easily implement repeated cubing idea. Yeah. So let me write it. Yeah. But just one more step. Yeah, because the cube structure, one more step. Yeah. And x. Yeah. We need two parameters, not one. Okay. Yeah. All right. Yeah. Initialization. Okay. Yeah. Power. Recursive function call cube. Yes. Yeah. X here. Okay. X here. Yeah. And over 3 integer division and x here. Okay. Yeah. All right. If n mod 3 equals 0, answer times okay, yeah. If one extra multiplication x times here you can see this part is common. You can use one expression to write it, right? Yeah. So you can save coding a little more. Yeah, but else if, right? Okay. And else answer equals x squared. Yeah, x squared, you need to do one multiplication, yeah, right? And the PWR, right? Yeah. And the return answer. Right? So you can see implementation recursively in this way. Okay. Yeah. So here, for repeat the cubing, this x squared, if you want to save a little more, yeah, a little more, actually, it may not be a big deal. Yeah, may not be a big deal. Yeah, because, yeah, that's one multiplication, one extra multiplication. You can think about save or not. Yeah, but think about when you try to save one multiplication here, if you need to do a lot of work, then your save may not be a good idea. All right. Yeah. So here, small discussion on, otherwise, you just do one multiplication for this x squared. Yeah. Because you can imagine if you want to save this multiplication, you may need to do a lot of work. So that means the save may not be worth the cost you pay. Okay, yeah, so that's another issue. Yeah. So then you just simple do an extra multiplication here, x squared. Yeah. All right, yeah. So that's the implementation. Okay, yeah. Recursively, yeah. All right. And then next, mix repeated squaring and cubing. Now we have both techniques. Okay, think about. Now I like to show you sometimes we can do better by mixing squaring and cubing technique. Okay, yeah, here, let me give you one example. The first one, x to the 15th. Yeah. Let's do repeated squaring first time, repeated cubing second time. Then we mix two techniques the third time, and we compare which one is better. Okay, yeah. The first time, repeated squaring. All right, yeah. X to the 15th, we can write x times x squared times to the 4th times 8th. That's the square structure, right? Yeah. In order to get x to the 8th, we need the 3 multiplications, right? And the 3 multiplications covers x squared, covers x to the 4th, right? So we do not need to do more than that. Yeah. After that, then these 3 dots, we need 3 more multiplication. So the total multiplications, 3 plus 3 equals 6. So that's the repeated squaring. Yeah. The second time, repeated cubing. Okay, all right. X to the 5th, this time we write it based on the cube structure. X to the 5th multiply x to the 5th multiply x to the 5th. All right. But we need to calculate x to the 5th first, right? Yeah. And when we calculate x to the 5th, we take the repeated cubing way. Okay, yeah. So what's that? Repeated cubing way. Remember, n mod 3 equals 2, right? Yeah, here, you know, n equals 5, so remainder is 2. So x squared times x times x times x, right? Yeah, yeah. So you can see, yeah, 1 multiplication, 4, okay? You use x to the 5th, you need a 4 multiplication, then 2 more here, 2 more here. So the total also, the total 2 plus 4 equals 6. The same as repeated squaring way, okay? 6. But you know, this evaluation is too slow, not the best, right? You can save. Yeah. So here, our method 3 mixed away. Yeah. Today the writing is very slow. Yeah. You know, my computer problem. Yeah. I need to restart before the class. Yeah. All right. Now let's redo that x to the 5th. Okay. Redo x to the 5th. But when we redo x to the 5th, we use the repeated squaring way. Okay, repeated squaring ways here, because m mod 2 remainder is 1, right? Yeah. Recall that recursion implementation in the previous slide. So we should write x squared, okay, yeah. This way, x squared, 1 multiplication, right? Yeah. And this one reuse, we do not need to redo it, right? So 1, 1, you can see for x to the 5th, we need 3 multiplications. Nope, yeah. 3 multiplications. Okay, all right. Then the total cube, yeah, because that, first time 15, so that's 2 plus 3 equals 5. 5 better than method 1, method 2, right? 1 multiplication fewer, 5. 1 fewer. Okay, yeah, better solution. And this is a mixed way. The first time we do the cubing way. Okay, the first split, we use the cubing way to do the first split. But our second split, we do squaring way, squaring split. That's the mixed way. Okay, yeah. Then you can do better. Yeah, think about it. In general, we need to mix squaring and cubing methods in a smart way. Sometimes this way, sometimes that way, smart way. Then you can get the best answer. Okay, all right, yeah. So that's the, these 2 smart methods I like to introduce to you. Okay, yeah, try to understand. Yeah. Then now, yeah, I have a few more minutes. I like to talk about question 10 of our quiz 1. All right, yeah. The problem is fixed, but yeah, when you answer that question, you need a knowledge from a few pieces of knowledge covered in this module. All right, yeah. So the P of x, the polynomial, is 1 plus 5x plus 10x squared plus 10x cubed plus 5x to the 4th plus x to the 5th, right? Yeah, okay, yeah. The first thing, the first knowledge piece you need, pay attention to these numbers. How special these numbers, the coefficients of this polynomial. How special they are, okay? Yeah. Can you associate these numbers to Pascal's triangle? Pascal's triangle? The first knowledge piece, you need to recognize its special structure related to Pascal's triangle. All right. After you can connect to it, the second piece, so this is the first piece, okay? The second piece, the binomial formula. because the Pascal's triangle related to the binomial formula. When you can apply binomial formula, so P of X based on the binomial equals 1 plus X to the 5th power binomial formula. All right. So that's step 2. Step 3, minimum number of multiplications to calculate power of 3. Did we do that before? Did we do X to the 5th before? Right? Yeah. See the previous slide. We did it, right? Previous slide, we did it. Right? Then you can answer this question. Here you can see you need to have sufficient knowledge in your background to answer this question. Okay? Yeah. These 3 steps are very important. Yeah. A little tricky, but all the techniques are covered, provided in this module. Yeah. So if you understand everything covered in this module, then still you need to do one thing. Even you know all these 3 things, you need to have another important skill. Connecting the dots. That skill also important. Yeah. For each individual step, you know, step 1, you know, step 2, you know, step 3, you also know, but you may not be able to connect the dots. How about that? That's another important skill you need. All right. Yeah. Here with this hint, then it's not very hard to answer this question. Okay. Yeah. All right. Yeah. So, yeah, I run out of time. Yeah. I cannot talk about the project. The project, yeah, here with only 2 minutes left, I can say a few sentences about the project. The reason I introduce these 2 techniques because I want to put repeated squaring implementation in project 1. Yeah, that's the reason. I plan to put, yeah, I haven't put it. I plan to put the repeated, not cubing, okay, only squaring. Repeated squaring, only one, this technique in our project 1. Okay, yeah. So you need to understand this technique. And the recursive function implementation, I give it to you. Okay, so you try to make it smooth. Yeah. Although you can improve it. Yeah. The basic idea is there. Yeah. If you like, you can improve it a little more. Okay. Yeah. And in project 1, you need to implement polynomial evaluation in 3 methods: method 1, method 2, and the method 3. All right, 3 methods. Yeah. Method 1, you know, all the way. Method 2, repeated squaring way. Method 3, Horner's rule way. How about that? 3 different implementations. So then you do comparisons. Okay, yeah. All right, yeah. So let me complete our lecture part E and the whole module 1 right here. So